Hi, everyone. Uh, can someone confirm whether they can hear me? Uh, can you hear me? Okay. Uh, can someone confirm whether they can hear me? Okay, okay. Thank you. Thank you very much. Okay, so my name is Aliyu Kasimu, and my presentation is on introduction to rail vehicle multibody dynamics. So I'll be talking about comfort, derailment, and some other things that are related to that. So first of all, as I've said, my name is Aliyu Kasimu. I'm currently an MSc student of vehicle engineering at Central South University. I finished my bachelor's degree in same university, Central South University, traffic equipment and control engineering. And in the same year, 2021, I completed the mechanical engineering degree at Ahmadu Bello University, Zaria. So my research interests include real vehicle multibody dynamics and computer vision for metrology. So we'll start with derailment analysis. So, uh, you know, whether you know derailment or you don't, you can see that the consequence of a derailment is devastating. Look at this picture, for example. Look at this picture, for example. This occurred in Hunan. So many people died. Here, this occurred in Washington, in the US. Although this is for freight train. So, but you can still imagine how many goods and so many the delays, the costs, in terms of the economic costs, the money that will be lost due to this derailment. This happened in Odisha. Odisha is a state in eastern India. So many people died. Over 100 people died. This happened in Texas in the US. This happened in Lagos. People either died or got injured. So derailment is a serious problem, and the analysis of derailments, becomes a very key issue for the railway industry. So briefly, very briefly, I'm going to talk about the mechanism of railway derailment. So first of all, the most common method for derailment analysis is the EN 14363. And it says that, number one, if you want to do a derailment analysis of any train, number one, the vehicle speed must be less than 10 kilometers per hour. That means you have a quasi static run, and the curve radius on which the train must run is 150 meters. So for you to now look at the derailment coefficient or the safety coefficient, you look at the ratio between the vertical force Y and the lateral force Y and the vertical force Q. So that ratio gives you a sense of what happens or what is happening in terms of the interaction between the wheel and the rail. So if you look at this, just trying to briefly explain the mechanism behind derailment. So imagine that this force is very great, and say for instance that it's greater than Q, then this part of the wheel is basically going to climb, right? To climb the rail. This is the wheel and this is the rail. So if you have a very great force in this direction, the wheel is just going to climb over the rail, and then it will get out of the rail. Once it gets out of the rail, all the other wheels following it will follow that. Other wheels will follow that, and then you have derailment. So or even overturn in some instances. So what are some of the factors that can make the Y become very large, so that you have a derailment? For example, crosswind, right? A crosswind can cause, a crosswind will affect the lateral component of force of the car body, whether it's a passenger or freight car. And then once there's a disequilibrium or inequilibrium, then you basically have a derailment. The second part of this is comfort analysis. And I'm going to do this presentation in the context of a presentation I gave last year at the Auto EI. So that's on coupled rigid vehicle multibody dynamics analysis of railway passenger ride comfort. So the first is research background. As I've said, this is based on a conference I presented last year at the Auto EI. So please don't mind this map. So what comes to your mind when you see headlines like this? Passengers who hang on trains to face suicidal trial. Another one is rooftop train riders to pay 100,000 fine. So this is trying to, discourage people, right, from riding on trains, on top of trains. And then another one is NRC increases the speed of the trains to 130 kilometers. So what comes to your mind when you look at some of these headlines? So I'm going to skew your thinking towards looking at the comforts of passengers in these trains. So look at these two pictures: the one in the green bounding box, and another one in the red bounding box. So which of the two groups are happy? If I ask you, is it the one in the green bounding box, the people in the green bounding box, or the people in the red bounding box? You can see that there is no facial, expression of happiness in this group. But here, you can see someone is smiling here. Someone is smiling and looks happy. But are they really happy? Are they really happy? Are they really happy? So, you can look at it objectively to say, will you be happier being in this situation or this situation? So let's dive into this and look at what makes more sense, objectively speaking. So what are the health benefits of mechanical vibration in humans? First of all, the vibration comes from the interaction between the wheels and the rails, right? What is the basic effect? So once you have vibration, from the perspective of the passenger, below 1 hertz, you have motion sickness. Actually, it's around 0.1 to 1 hertz. You have motion sickness. When you have above 1 hertz, but less than 6 hertz, you have alerting effects. There's a range where you have chest and abdomen pain. And if it's up to 90 hertz, you have degradation. It can cause a degradation in visual actions. So what is the methodology for this presentation? Before I dive in, I'd like to introduce you to the sense of orientation as far as railway is concerned. So the direction of the running of the train is known as longitudinal direction. Now the direction along the track gauge or the track width is called the lateral direction, and the direction along gravity, that's up or down, is called the vertical direction. Now, if the vehicle rotates about the vertical direction, that's the yaw. If it rotates about the lateral direction, that's the pitch. If it rotates along the longitudinal direction, we call it the roll. Now, all these possible, all these motions are possible within some range of magnitudes. So this mechanical human ride comfort model, gives you, it's a mechanical model that shows you the frequencies, at which different components of the human body resonate to mechanical vibration frequencies that come from the interaction between the wheel and the rail. So, it gives you a sense of what happens. So if you take, for example, the shoulder girdle, so we're just saying that if vibration, mechanical vibration around 4 to 5 hertz is transmitted to the human, the most sensitive or the most critical component of the human that will feel that is the shoulder girdle. So, and it's the same thing for all of this. And for whole body vibration, WBV, the range of frequencies you have is between that discomfort happens or comfort happens is between 1 and or 0 and 1 hertz and 100 hertz. So traditionally, railway passenger ride comfort is analyzed using 3 methods: the continuous index, the Stirling index, and the mean comfort index. So I've given a workflow around most of them. So the first is you obtain acceleration data. Now, in terms of the continuous index and the Stirling index, and even sometimes according to literature, the mean comfort index, you collect acceleration data from the floor, a position on the floor of the car body under the passenger seat. Especially for Stirling index, which is mostly used in China for overall as an overall mechanical vibration index for the car body. You install a 3 dimensional acceleration sensor on the car body, and then that will measure in X, Y, and Z, as we've talked, as we've just explained previously. So after you obtain the acceleration data, you apply a low pass filter, 0 to 100 hertz, and then you digitize it. So digitization means that you are looking at when you look at the time history of these acceleration data, you divide them into blocks of 5 seconds, or more, depending on the rules of the method you're using. And then you calculate the two-sided square acceleration. You do frequency weighting, and then you pick the 95 percentile acceleration. We are doing this because we want the most significant discomfort to be identified as the comfort level. Because if you don't do that, so for example, if at the entire block range that you've picked, we don't have very significant vibrations, or we just have a few points of very significant discomfort, then you're not going to get that, because you just take the average. But if you do a 95 percentile, then you're going to consider the most pronounced discomfort levels. And then from there, you apply the calculation. In terms of mean comfort index, you use the NMV rule. The continuous index is actually used sometimes for the evaluation of comfort in curves, considering the centrifugal acceleration that occurs on curves. So these are basically the equations that go into that. For every you create a 5 seconds window, and then you digitize the acceleration time history based on that. So at the end, if you get if the resultant acceleration is less than 0.2, then we say that is very comfortable for the ride, that the passenger ride comfort is very comfortable. So it's very convenient for the passengers. If it's greater than 0.2 but less than 0.3, then it's comfortable. If it's less than 0.4 but greater than 0.3, then it's medium. And if it is greater than 0.4 meters per second squared, then it is less comfortable, and you need to do maintenance and look at the issues for the reasons why passengers are feel some a significant amount of discomfort in their ride when riding the train. The mean comfort index, as we just explained, is the 95 percentile of the 5 seconds RMS on floor level. We explained this. So you basically get the discomfort levels in all the directions. This is for X direction, this is for Y direction, this is for Z direction. You square them, you take their square root and multiply by 6. You have the overall the overall comfort levels for that particular train and for that particular point or location where you installed the acceleration sensor. So when the overall comfort level is less than 1.5, it's very comfortable. If it's greater than 1.5 but less than 2.5, it's comfortable. If it's greater than 2.5 but less than 3.5, it's medium. And if it's greater than 3.5 but less than 4.5, it's uncomfortable. But if it's a level above 4.5, then we say it's very uncomfortable. And this means that the railway industry must urgently look at the issues. So, the assumption usually that we make is when using the multi-body dynamics approach to evaluate passenger comfort is that the car body is rigid. If it's rigid, then it has 6 degrees of freedom. However, we know that although the deformations for such large components like the car body, the deformations might be low or might be small, but they are still deformations, right? So what if we consider the deformation? What if we consider the deformation? Instead of considering it as a rigid body that has only 6 degrees of freedom, how about we consider it as having more degrees of freedom? And when we do that, what is the effects on the evaluation of comfort? So first is, to make it flexible, to make the car body flexible, you do a structural mesh. After then, you denote the interface points, you attach the couplings, you run the Craig-Bampton reduction on that. You retain the critical degrees of freedom at those interface points. You retain the respective nodes, and then you convert that file into an FBI generation, an FBL file, which will work in SIMPAC from Abacus, for example. And then it becomes a simple in SIMPAC flexible body that you can use, to replace the hitherto, utilized rigid body model. And then from there, it becomes a SIMPAC system model that you can run simulations on, virtual prototyping simulations, and get results. So usually we use Hypermesh or Abacus, and you can use other tools also like ANSYS to do the flexibility modeling. And for this model, what I'm presenting now, after the flexibility modeling, we had over 1 million mesh elements and over 1 million mesh nodes. And we had also 2 master nodes. You can see the master nodes here. One is here, and another one is here. Just at the interface point between the car body and the bogie. So the results. Before we talk about the results, let me talk about the locations where we installed or where we tested the discomfort levels for this virtual prototyping simulation. So we put one here, put one in front, one in the middle, and one at the rear. And then you can see that it is a 3D accelerometer that we used for each of those locations. So what is the influence of speed on passenger comfort? So you can see that there's a linear relationship between speed and passenger comfort. If you remember one of the headlines I showed previously, that the NRC, for example, increased the passenger train speed to 130 kilometers per hour. Then when you look at this picture, you immediately see the influence of speed on passenger ride comfort. So basically, you are saying it's a linear relationship, right? If you increase the vehicle speed without touching any other thing, without improving the suspension systems, without putting any new suspensions on the passenger seats, if you leave everything as it is, and the only variable you vary is the speed, then this is the result you have. You have that the more you increase the speed, then the discomfort levels grow up also. So if there is an increase in vehicle speed, then generally there will be an increase in passenger discomfort. So we plotted this, although the previous chart is more clear, but if you are more critical, you can see, for example, that we plotted the comfort index against speed and against the comfort in different directions. But for NMV, which is the overall comfort index, you can see that the greatest magnitude of discomfort occurs here. And if you trace this line up to the speed axis, you'll see that it's the highest. It's the highest. So it's just the same trend for all the direction also. But there's something also you may want to note. That the discomfort in the vertical direction is more pronounced, and this is proven from other literatures also. So we can conclude from these two charts that when you decrease speed, then you can increase comfort. And when you increase speed, then you decrease comfort directly or indirectly. Track severity. I want to also consider the effect of, or the influence of, track irregularities on passenger comfort. The greater the severity of the track irregularities you have, then the more vibrations you're going to have in the wheel-rail interface. If you have more more mechanical vibration in the wheel-rail interface, then you are going to have greater magnitudes of mechanical vibration that is transmitted to passengers that are on board the car. So I chose 3 different kinds of tracks based on the severity of their irregularities. So you can see that the track 1 and track 3 are the most severe, right? They're the most severe because look at it. I plotted the acceleration PSD against the frequency. So you can see that the acceleration PSD of the 2 track, the red and blue, that is track 1 and track 3, are in the highest. This means that they are the worst track among these 3. They are the worst, and the green one is an ideal situation where you have no irregularities. That means you have a perfect track surface. So when I simulated this, you can see that directly, the relationship is very direct. You have high for the tracks that have very severe irregularities. You also have they're the severest here. So they cause the greatest amount of greatest magnitude of discomfort. So that means what does this tell you? It tells you very directly that when you are very prudent, and very, if you are focused on track maintenance, then you will have if you are not focused if you are not focused on track maintenance, if you don't do track maintenance, then you're going to have very high levels of track discomfort. While if you do your track maintenance very well, then discomfort of passengers will go down. So I think that directly what we are talking about is the maintenance operations that we usually do for tracks and wheels, right? For example, grinding, the track grinding. So if you grind and the track moves closer to an ideal perfect surface track, then you're going to have higher levels of comfort from passengers. So now, all what we've talked about now is based on the rigid consideration that we are considering the car as a rigid body. How about considering it as a flexible body? So these are the eigenvectors. Basically, we're saying that at every frequency, this is the mode shape of the car, right? So you can see that the minimum is 9.47 and the maximum is 38.46 hertz. So when you wax this, you'll see that, you know, you can see you compare the rigid and the flexible body, you'll see that, you know, they're very similar. Although, if you pick the flexible situation as the standard, then you can, you know, conclude that the rigid body consideration, you know, overemphasizes the ride comfort, right? However, if you pick the rigid consideration as the standard, then you'll see you can conclude that the flexible situation under emphasizes, you know, ride comfort. But, you know, the critical point here to look at is that the values are very close, right? So that means there is negligible influence of making the car body, or considering the car body as a deformable body with elasticity, as far as the evaluation of comfort is concerned. So you can see, we can conclude that the comfort value when flexibility is considered is reasonable. That means they are very close. So for my conclusions, you see that you know very immediately that that increasing speed reduces passenger ride comfort. That bad track maintenance culture reduces passenger ride comfort. Also, that car body flexibility has significant effects on passenger ride comfort. That is, if you consider it as a standard, or you consider that as and you compare. But overall, you know, the values, or the range of values are within the same brackets, or the same you know, comfort index category. So you don't really, so that means you know, a ride comfort does not become discomfortable, you know, just because you make it elastic, you make the car body elastic. The last conclusion is that skilled locomotive engineering researchers can be drafted into research units within NRC or any other, you know, railway industry to study the effect of changes in vehicle or track operations policy, so that when the policymakers, you know, make policies like, okay, increase the train running speed, you know, if they have a research unit, you know, that can advise them competently, you know, they might want to, you know, think twice about some of these policies. This is the end of my presentation. I thank you very much for your attention. So if you have any questions, you can please feel free to ask. Any questions? Okay, yeah.
Hi, Kasimu. Can you go back to your the finished element model here, for the car body?
Sure. I have to share my screen again. Okay, can you see my screen now?
Yeah.
Okay.
Let me see. Maybe
This one?
Yes.
Okay.
This is a flexibility model.
Yes.
The flexibility is that you consider the car body as a flexibility structure.
Yes, as a flexible as a flexible component instead of a rigid one that only has 6 degrees of freedom.
So what is the master node?
I understand your question. The master node is the interface point, you know, the point of connection between in this case, between the car body and the bogie.
The bogie.
Yes.
The bogie is a rigid body.
It's rigid, yes.
Oh, so it's a connection between a rigid and a flexibility.
Flexible, yes.
Yeah.
Yes.
Okay.
Yeah.
Understand. Thank you.
You're welcome. You're welcome. Are there any other questions? You can raise up your hand and I'll allow you to speak. I'll wait for 5 seconds, and after 5 seconds, I'll assume that there are no questions. Okay, everyone, in the absence of no other questions, in the absence of any other questions, I would like to thank you very much for coming, for listening to me, for sharing your time with me and so on and so forth. Thank you very much, and this is the end of the session. Bye.